So let's look at the travel cost method. As the name suggests, the travel cost method uses people's travel as a way to deduce their valuation of the environment. Good thing about the travel cost method is that people like to travel, or at least they used to, and therefore there's lots of data. And the reason that people like to travel is because they like to visit beautiful places that you see depicted here. And the travel cost method was proposed originally by Harold Hotelling, who we've come across before. He is the guy who first gave the first analytical proof of the first and second welfare theorem, and he's of course also known for his work on the pricing of exhaustible resources like oil, and for his work on the spatial feature of markets. But also in this letter that you see fully displayed here, he proposed the travel cost method while writing to the director of the National Park Service. And let's look at the crucial paragraph. Let concentric zones be defined around each park so that the cost of travel to the park from all points in one of these zones is approximately constant. The persons entering the park in a year, or a suitable chosen sample of them, are to be listed according to the zone from which they come. The fact that they come means that a service of the park, that's a typo there. The fact that they come means that the service of the park is at least worth the cost, and this cost can probably be estimated with fair accuracy. If we assume that the benefits are the same no matter what the distance we have for those living near the park, the consumer surplus consisting of the difference in transportation costs. The comparison of the cost of coming from a zone with a number of people who do come from it together with a count of the population of the zone enables us to plot 1 point for each zone on the demand curve for the surface of the park. By a judicious process of fitting, it should be possible to get a good approximation of this demand curve to provide through integration and measure of the consumer surplus resulting from the availability of the park. It is this consumer surplus, calculated by the above process with deduction for the cost of operating the park, which measures the benefit of the public in that particular year. This, of course, might be capitalized to give a capital value for the park, or the annual measure of benefit might be compared directly with the estimated annual benefits on the hypothesis that the park area was used for some alternative purpose. And that's the travel cost method in a nutshell. Hotelling here describes the entire process of the zonal travel cost model. And it's as simple as that. So the basic idea here is that you can calculate, or you can use the time and money that people spend to get to a particular place as a way of an entry cost. And the suggestion here is that if that entry cost is low, that is, if you live near a park, then you will visit it often. Whereas if you live far away from the park and therefore you need to spend a lot of money and time to get there, you will visit less often. And this is essentially a demand curve, and you can use the demand curve to estimate a consumer surplus. That's essentially what Hotelling is saying here. And you can apply this to all sorts of things. You can, of course, just close the park completely, and then you have an estimate of the total consumer surplus. You can also hypothetically open a park that is very similar to an existing one. You can change the quality of a particular park. You can change the access costs, and all that will induce a change in the demand for that park, and therefore by integrating under the relevant portion of the demand curve, you can estimate the change in consumer surplus. The process that Hotelling describes is a so-called zonal travel cost method. I'll talk about it more in detail, but you can also do this where essentially every zone contains one individual. And the key thing that we predict with these models is how many trips are made to a particular site by a particular individual or a particular population of individuals at a particular cost. But the key thing here is the number, the key prediction here is the number of trips made. And then later I'll talk about what to do if there's multiple sites. And then you need slightly more complicated econometrics to get there. So how does this work in theory? We assume that there is an individual who seeks to maximize her utility by consuming two things. One, a composite commodity X that contains everything else that we care about. And second thing is a recreation service. It's not a good because you don't consume it, right? It's a service. We want to maximize that particular utility, and there's two budget constraints. One is the total income that you have is a function of the time spent working times the wage that you earn. We normalize the price of the composite commodity to 1, so this is part of your expenditure, and the other part of the expenditure is how often you recreate times the cost of recreation. This is your money budget, and then you have a time budget as well. Total time spent working, and then this is the time spent on recreation, where TR is the time you need to visit a particular park, and R is how often you do that. So this is our decision problem. We can simplify it a little bit if we introduce P, which is the total cost of a trip, and total cost of a trip P depends on the money spent on getting there. That's the entrance fee and the parking fee and the petrol if you travel by car. Plus the opportunity cost of time. So TR is the time that you spend to get there, and then we assume that people are rational at the margin and decisions they make about working are such that everything is in equilibrium, and that means that the opportunity cost of time is just your marginal wage. So this is the time spent. This is the wage that you otherwise would have earned had you not spend time frolicking in the park. This is the money you would have earned, right? So this is the opportunity cost of time. These two equations we had before. This is your money budget. This is your time budget. This is the what I just explained, the total cost of the trip. If we bring WTR to the other side of the equation, and multiply everything by R, then this equation becomes this equation. So now we have an expression for CR. So we plug this into here to get this expression that we have here. And then we bring WRT to the other side of the equation and substitute this in, and then what we have is a total budget constraint, where total income, so the wage that you earn minus the opportunity cost of what you could have earned, is your total cost for spending on recreation and your total cost on the composite commodity, the other things that you care about, your material consumption. So essentially what we do by introducing this total cost per trip is that we combine the two budget constraints into one, which makes the optimization process a bit, the optimization problem a bit simpler. and easier to interpret. So we want to maximize utility, subject to this budget constraint, so we form the Lagrangian. Let me see here, where lambda is the shadow price, and then the first order conditions are that du dx should equal 0. So this is just marginal utility, how much you gain from consuming material goods, and that is just because the price is normalized to 1, that is just equal to lambda. And du dr is essentially this wt just dropped out. This is lambda times p times r, but then we derived it to r, so that becomes lambda p. So essentially what this says is that the marginal utility of material consumption should equal the shadow price of that consumption. That's an equimarginal principle. And the marginal utility of recreation should equal its shadow price. So essentially what we do here is show that recreation is just a standard consumer good, and the ratio of marginal utilities of recreational consumption relative to other consumption is just the relative price of that, because if you divide these two, then lambda drops out, and we just have the relative price of recreation. So this just fits standard in your standard micro theory about demand. There's nothing special going on here. And that means that we can just do all the things that we would do with standard consumption goods. So here we have a hypothetical demand curve where if the price is 12 pounds per trip, then you would take 10 trips. Now, if the price goes up, you would take fewer and fewer trips. And if the price goes down, you would take more and more trips, right? And this particular example also assumes that if the price goes to 25, you would stop going altogether. Then it's just not worth your while to go to this particular place at all. This is a purely hypothetical example. But it shows there's a demand curve for recreation, and you can just use it like any demand curve. And in this case, we estimate the total consumer surplus. Where the key thing here is that if you drive up the price of access to this particular park to 25, then you would not go at all. Which of course is the same thing, if you're only interested in use value, as there being no park altogether, right? If the park is prohibitively expensive, then you wouldn't go. If the park is not there, then you wouldn't go either, and the two are equivalent in terms of use value, right? And that's an important thing to keep in mind if you want to estimate the total value of something. So how do you do this in practice? In the zonal travel cost method, you have a site, a park that you're interested in. Then you create zones around it for which, as Hotelling suggested, the cost of travel is approximately constant within that zone. Then you look at for each zone how many visits there were. So this could come from a survey of the visitors to that park, or it could come from administrative data. Of course, nowadays everybody pays by card when they visit, so it is very easy in principle for the bank or for the park authorities to find out where people are from, right? But let's assume that we have this data, right? This is the number of visits from each zone. This is the population in these zones, purely hypothetical example. And then you can work out, of course, the rate of visitation, which is 15,000 over 2 million, right? This is your relative visitor number, which is actually more interpretable. And then the travel costs. So the people in zone 1 live very close, so their travel cost is low, and then the travel cost goes up if you move further and further out, right? Calculate the visit rate, as I said, and then you run a regression of the visit rates on the cost, and if you use OLS and these particular data, then what you would find is that your R is some sort of constant. There's always a group of people who would come, and as the travel cost goes up, you have fewer and fewer people visiting this park, right? And so the higher C, the lower the relative number of visits, and then you multiply that with the population in the zone to get the predicted number of visits. And then you can play around with your travel cost. In this case, what we do is we impose a parking fee of £5 or an entrance fee of £5. And then what we have is that the R falls, right? C goes up, so R goes down. And we predict an R, and based on the number of people there, we predict the number of visits. And what we have here is that for zone 1, if we impose a £5 charge per person to visit the park, the number of visits goes from 15,000 to 12,000, in zone 2 from 48,000 to 36,000, and so on and so forth. And again, for the furthest zone, zone 5, the price of 35 actually exceeds the choke price. And for these people, essentially visits drop to 0. And for these people, it might as well have been as if the park were not there at all. Right? So this is exactly what I did. And of course, you can play around with different numbers altogether. And this is the predicted number of visits. If we play around with the fee more, if the current situation is that no admission fee, the situation with the £5 fee you just seen, and if we drive up the admission fee further, the park becomes more and more exclusive, fewer and fewer people visit, and it goes, the entrance fee goes to 25, and we actually predict that nobody would visit at all, right? And this is just as you would expect a demand curve to work, right? So these are the points I've just drawn on this. You can then integrate under this particular curve to find the total consumer surplus of this particular park, which is entirely hypothetical, right? The consumer surplus is about 1 million, slightly more than that. So that's how it works. Of course, there's all sorts of things that we assumed here, apart from the data that we made up. You can play around with the functional form of the demand curve. Previously, I had that R is a function of C, but you might as well assume that ln R is a function of ln C, or any other functional form that takes your fancy. And of course, the question here is which is the which describes the data best, right? And of course, different functional forms will give different results. The technique we used for estimating the particular curve is ordinary least squares, which is actually not correct, because ordinary least squares works just as well. Or ordinary least squares assumes that you can have positive as well as negative responses. Essentially, it draws a linear curve, and that curve might go negative, because that's what linear relations do. So you actually should have used the Tobit model, which sends us around 0. That's a technicality. Now, the zonal travel cost method assumes that everybody in a particular zone is identical, and you essentially look at aggregate visitor numbers. What you could also do is look at individual travel behavior. And there's tons of surveys out there, one or two per country, that actually ask people, interview people, where did you go to enjoy yourself over the last week or over the last month. And then you actually have the individual travel choices, and you can look up how often somebody visited the Kew Gardens, for instance. That data is actually there. If you have that data, you can calculate the distance or calculate the geographical distance from where they live to where they went using geographic information systems. You may also have a more fancy survey that actually tells you how people got there and how long they took, whether they took the bus or the metro, or whether they cycled there or drove. That information is actually available in some surveys, not in all. The good thing about this is that unlike the zonal travel cost method, you actually also have information about people's income and age and gender and whatever matters for these decisions, family composition being an obvious one. If you use the zonal travel cost method, then you have just a bunch of people, and you can assume that people are equal to the average of their zone, but that is a pretty hairy assumption. And the good thing about the individual travel cost method is that you can actually include the characteristics of the people who do the traveling, and oftentimes they are different by characteristic. Where particularly people with children behave very, very differently than people without children in terms of their travel choices. So you can include all this. The principles are exactly the same. There's all sorts of things that are less than perfect with these travel cost methods. The most important thing is that the demand curve that we just estimated looks at the price in terms of travel time and travel cost of only the site of interest. And that immediately assumes implicitly that competition doesn't matter. And really, it does. The reason that people may not go to a particular park may have nothing to do with the quality of that particular park, but it may just be that there's much better parks nearby, or vice versa. People may go to a particular site because there are so very few alternatives, not because they particularly like it. And that is hard to do, or it's impossible to do with the traditional travel cost method. And I'll come back to an alternative that actually does this better. And because you look at an individual site, it's impossible to include site quality because there's nothing to compare. Multi-purpose trips are difficult. And in some cases, people specifically travel to a specific site. That's the only reason for their trip, and then all their cost is attributable, all their travel time and all their travel expenditure is attributable to that particular act of recreation. But sometimes people go to a particular place and then decide to go do a bit of shopping in the neighborhood or visit another site that might interest them that is in the neighborhood. And then, of course, you need to somehow apportion the time and money spent traveling to site A, B, and C that are near, but that all are combined in a particular day trip. And that makes it difficult to have much confidence in results unless you have detailed knowledge of why people travel to a particular place. And if you do surveys of that sort, then you would actually find that people have difficulty giving precise numbers there, and of course people often travel in groups, and then some people in the group will tell you, no, this museum was the main reason that we're here, whereas somebody else in the group will say, no, it was the playground that we're here. It's probably the children that will tell you that, or somebody will say, no, it's the shopping that came with this. That is the actual reason that we're here, right? So that makes it fairly difficult to interpret the results. The standard travel cost method just has a cost, right? And it assumes that there is money spent on a particular trip, and there's time spent. Some trips are much more pleasant than other trips. You can imagine traveling to the beach on a hot day in an overcrowded, very hot train, and then the journey really is a cost. But you can also imagine traveling to the same beach in an open-top car with three of your best friends. And then, of course, the trip actually becomes part of the fun rather than a real cost. And those things should be taken into account, but oftentimes you don't have data for that. For the opportunity cost of time, I just assume, well, that's your wage, right? It's maybe true at the margin for people who sort of like work in an occupation where you can freely vary the hours that you work, or more importantly, where you can freely vary the hours that you work and also earn different sorts of money depending on that. But very few people are in that particular situation, and labor markets are often regulated and often lumpy and everything. So to use the wage rate as the opportunity cost of time is a pretty strong assumption. And of course, it does not apply at all to people who, for whatever reason, are out of work, right? Either because they're students, or because they're retired, or because they're unemployed, or because they're disabled. And for those people, the average wage is a very poor approximation of their opportunity cost of time. And of course, pensioners do travel quite a lot. And as I said, people with children tend to visit parks and those sort of things quite a lot. And if they're sort of taking time out of work to take care of their young children, then the notion of using their wage as the opportunity cost of time is a bit of a strong assumption. And then finally, of course, but this is true for all revealed prevalence methods, this is not particularly the travel cost method, you can only use this to value direct use values. People go to the beach, people go to the park to enjoy themselves, and the time and the money that they're willing to spend on that reflects their direct use. It does not reflect the existence value of the park or the existence value of the beach, or the fact that their children might go and enjoy themselves there at a particular point in the future. No, that is not included in this at all. It's the direct use value only.